Now that we have our environment fully set up, let's get the player ship moving under our control. To do this, we need to write some very simple code. We will be writing in C#, which is one of the 3 scripting languages supported by Unity. To stay organized, we need somewhere in our project to store our new scripts. Let's add a new folder to the root level of our assets folder. It's worth noting that this folder could be placed anywhere within our assets folder to work, but for clarity, it would seem that the root level is the best location for such an important folder. Select Assets to make sure that we build this folder on the root level. Otherwise, we will have to move it after we have created it. Use the Create menu in the project view and select Folder. This will create a new folder in Assets. This new folder will automatically make itself ready to edit. Let's change the name to Scripts, and hit Enter or Return to accept the change of the name. Now let's create and add a new script to our player ship. I'm going to quickly reduce the view of these referenced materials shown at the bottom of the player game object by clicking on the header bars. This will make it easier to view and access the Add Component button without scrolling. Next, let's click on Add Component and select New Script. This will allow us to create and add a new script directly onto our player game object. Now, let's set the name of the script to Player Controller. I feel it's best that we follow the convention of capitalization shown here, with a capital P and a capital C. Script names should start with a capital letter, and the camel casing of the name with the capital C makes the name easier to read. Once we have chosen a name, we can click on Create and Add, or we can simply hit Return or Enter to create and add this script. When we create a script in this manner, the script will be created on the root level of our project. We need to drag and drop it into the Scripts folder to file it away properly. Now, open the Scripts folder to view the script. Let's open the script for editing. We can do this in a number of ways. One way is to select the script, and in the inspector choose Open. This will open the script in MonoDevelop. MonoDevelop is a companion application that is bundled with Unity. This is the default script editor that comes with Unity, but you can use different script editors if you choose. For more information, please see the details on using Unity with other editors linked below. Before we start, I'm going to remove the sample code. We will be moving our player's ship using physics, so we will need to use the fixed update function. For more information on both update and fixed update, and how to use them, see the information linked below. So now, let's write some code. Write void fixed update. Fixed update will be called automatically by Unity just before each fixed physics step. All the code we put inside the fixed update function will be executed once per physics step. So write float move horizontal equals input get axis horizontal, and float move vertical equals input get axis vertical. This code grabs the input from the player. The axes horizontal and vertical are default axes that are preset in the input manager. Next, we need to apply that input to the player game object. We are going to move the player game object using physics, and we're going to do this by affecting the velocity of the game object directly. Now, this will result in non-realistic physics behavior, but hey, that's alright, we are making an arcade game. If we want to make a game that works properly with Newtonian physics, we would approach this code differently. The rigidbody component, which we attached when we set up the player game object, is how we work with the built-in physics engine. The rigidbody includes properties like use gravity, mass, and drag that we can pole, affect, and manipulate. So if we want to change the physics velocity of the player game object, we do this by addressing the rigidbody component. So let's write rigidbody.velocity. Now, rigidbody velocity uses a vector3 value. This gives us the direction we are traveling and how fast we are traveling as a vector and its magnitude. For more information on the vector3 class and vector maths, please see the details linked below. So our rigidbody velocity will be equal to some vector3 value. But what? Well, as we know, a vector3 is made out of 3 float numbers, an x, a y, and a z value. Well, what do we put in these 3 float values? We want to use our player input. Let's walk through this one step at a time. How much do we want to move on the y-axis, or up and down? Well, none. So y equals 0.0 f. And if we write it this way, 0.0, we need the f to indicate to Unity that this decimal value is a floating point number. How much do we want to move left to right? Well, that's our move horizontal. Copy move horizontal and paste it over the x value. And forward and back? That's the value from move vertical. Copy and paste move vertical. So how can we use this vector3 now that we've made it? One way is to create a vector3 variable. Let's call it movement. And movement is equal to a new vector3, move horizontal 0.0f, move vertical. In C#, we must remember to use the new keyword here. And our rigid body velocity is equal to movement. Now let's save this script and return to Unity. The first thing we check is the console, to make sure that there are no errors and that everything we wrote has compiled properly. If there were an error, we would also see this error in the footer, as our most recent error or message will always be shown in the footer. Let's test our code. Save the scene and enter play mode. We can move our ship, but it's moving very, very slowly. This is because input getAxis only returns a number between 0 and 1, so our ship's movement with this code will never be more than 1 unit per second. Let's exit play mode and return to our player controller script. We need control over our speed, so let's create a new public float variable called speed. This variable will hold a value we can use to multiply our input with. As our input will only be a value of 0 to 1, by multiplying our input by speed, we will be able to move our ship from 0 up to a maximum of our speed value. Now, multiply our movement value by speed. Let's return to Unity. We did not assign a value to speed in our script. Because we made speed a public variable, we can see it, we can set it, and we can change its value in Unity. Let's look at our player controller component. We can now see an editable property called speed. Let's change its value to 10. Now we save and play, and now we can move much faster around the game area. 10 times faster, as a matter of fact. But we have a problem. And that problem is our player ship can leave the game area. We have no idea where the ship is gone, and it would be very easy to completely lose track of where our ship is. We need to constrain the ship within the game area. So leave play mode and return to our player controller script. We are moving our ship by setting the rigid body's velocity. We can constrain the ship by setting the value of the rigid body's position. Again, this won't give us realistic physics behavior, but in our case, it's not necessary. Unity executes our code within a given function, one line at a time from top to bottom. The code we have written moves our player ship. We will write code that will come after the code that moves our ship, and if we have moved outside of the game, the code will set the player's position back to the edge of the game area. Because Unity will read and execute all of the code in our relevant functions before updating the frame, the ship itself will never leave the game area. So let's write rigid body, position, and this is the property we want to set, and then write new vector3, x, y, and z. And this is the value we want to set it to. The code we are going to write next will make one very long line. So I'm going to break this code over several lines vertically. This will all be the same instruction to the compiler. I'm going to follow the same indenting and bracket conventions that we are already using for organization and readability. Let's think about how much we want to limit our movement. How much margin do we want up and down? None. Our player game object should never leave the plane of the game. The y value? Let's set this to 0. But what about left, right, and forward, back? The ship is moving along the xz plane, and we want to clamp it within the game area. The ship starts at origin, or 0, 0, 0. So we want to set limits on all 4 directions along the xz plane. Let's return to our script. So write mathf. What is mathf? Well, let's look this up in the documentation. And remember, the shortcut to Unity's scripting reference in the documentation is Command plus single quote on the Mac and Control plus single quote on Windows. Mathf is well worth remembering. It is a collection of really useful, easy-to-use math functions. These include variables like epsilon, infinity, and pi, and functions like sine, cosine, tangent, square root, power, ping pong, repeat, and even Perlin noise generation. What we are looking for is a function called clamp. Clamp will clamp any given value between a minimum and a maximum value. We will use this to clamp the position of our player's ship into our game area. Returning to our script, let's write clamp rigidbody position x, xmin, xmax. And for z, let's write mathf clamp rigidbody position z, zmin, zmax. This will effectively clamp our position between the values we set for our min and our max on the x and z axes. Now we need to declare our min and max values. At the top of our script, write public float xmin, xmax, zmin, zmax. And using this format, we can define all 4 float variables on one line of code. Save the script and return to Unity. Let's look at our player controller component on the player game object. We can see these new properties, but to me, they seem to take up a large amount of space in the inspector. Moreover, these properties can only be used by this script. There is a way that we can both clean up this code and make it reusable. That is to put these into a separate class of their own. Let's return to our script, and let's move these into their own class. We start by defining a new class with public class, and then we will name our class boundary. We will follow these with brackets to hold our code. It's worth noting that this class will not inherit from anything like our player controller class does. The mono behavior that comes after the class name in our player controller class indicates that this class is inheriting from mono behavior. For more information on classes, inheritance, and mono behavior, please see the information linked below. Next, let's move our variable definitions from player controller to boundary. So how do we use this new boundary class? First, we need to make an instance of it in our player controller. So write public boundary, and note the capitalization. Boundary with a capital B is our type, as defined by the class name. Boundary with a lowercase b is the name for our reference, in the same way that speed is the name for our float variable. Next, we need to update our clamp code to reflect the changes that we have just made. Xmin is now part of our boundary class. which we access through the reference that we made to our instance by using boundary.xmin. This is true for xmax, zmin, and zmax as well. Let's make our code neat and tidy by aligning our indents. Save the script, switch back to Unity, and let's look at the updated component. Now we can't see our new updated properties at all. This is because the new class that we have created is unknown to Unity, and is therefore not serialized. Serializing is a way of storing and transferring information. Serialization is a complicated issue. At this point, just understand that Unity needs to have properties serialized to view them in the inspector. So let's switch back to our script. To serialize our new class, we need to use system.serializable in square brackets on the line before we declare our class to make sure that the class is serialized and therefore visible in the inspector. Save the script and return to Unity. Now, if we look back at our player controller, we can see boundary. Turn down the gizmo and we can now see our properties in an easy-to-use but very tidy container. We can also use this class in other places in our game. Now that we have our properties available to us, let's set their values. Make sure that we have the player ship selected. So what values do we need to set for xmin and xmax? Simply drag the ship to the edge of the game area and note the values on the x-axis. These seem to be about -6 and 6. So let's set these values to a good round -6 and 6. Doing the same thing along the z-axis, that's about -4 along the bottom. But along the top edge, we don't really want to give our player access to the entire upper game area. We will need to give the hazards in our game some room to be able to enter the game area. So let's back off a little bit, say about 7 or 8. Let's make zmin and zmax -4 and 8. This will give us a square playable area in our game, and reserve a little room for hazards at the top. Now, let's reset the player's transform, and let's test. Enter play mode, and we can see that we are now clamped inside the game area. Exit play mode. Now we are essentially done with our player game object, but I think it's worth adding one bit of fun to it before we move on. Let's add some bank or tilt to the player ship when we move from side to side along the x-axis. Switch to our script, and let's create a new variable to hold our tilt value. Next, after the code we have written, but still in fixed update, write rigidbody rotation equals quaternion Euler. And yes, it is pronounced Euler, which is also an x, y, and z value. For more information on quaternions and quaternion Euler, see the links below. We only want to tilt or bank along the z-axis, so x and y are set to 0. And z? We want the tilt along the z-axis to be related to how fast we are moving left to right, so our rotation on the z-axis is equal to our rigid body velocity x, which is our velocity from left to right, multiplied by our tilt factor, so we can control the maximum amount of bank. The only correction we need to make to this code is to multiply by negative tilt. Otherwise our ship will tilt in the opposite direction to what we want. Save the script and return to Unity. And let's set the tilt value. Let's try 3. If we feel it needs to tilt more, we can simply adjust the tilt property with a higher value. Let's try 4. 4 feels good. Incidentally, when the ship is banked over, it picks up a good combination of our fill and rim lights on the left side. That completes the code for moving our player's ship. In the next assignment, we will continue with our gameplay by creating shots for our player to shoot.